Hello. In this video, we're going to look at what happens when we have a system of equations, and we're going to look at a couple methods of solving. That would be graphically and by an algebraic process known as substitution. But before we get into a system of equations, let's actually consider what we know about a linear equation. So we're going to consider the line that is represented by y equals negative 2x plus 7. And I just want to answer the question, is the point 1, 6 on the line? The easiest way to verify if that point is on the line is to check if this particular x value and this particular y value, so in other words, if x equals 1 and y equals 6, do those values of x and y make this equation true? So is it in fact true that 6 is equal to, and I'm going to put a question mark here because I don't know that they're equal yet, I haven't verified, is that equal to negative 2 times 1 plus 7? Well, negative 2 times 1 plus 7 is 5. So this is actually not true. So then the answer is no. If I want to find any 3 points that actually are on the line, and in fact, I would only need 2 points to sketch the line, but we're going to do 3 just to be thorough. I can pick either a value of x or a value of y and calculate the corresponding value of the other variable. Now, this equation is set up in such a way that it's easiest to pick values of x. That's why x is considered here the independent variable. And then from that, calculate values of y, because y is the dependent variable. It depends on the value of x. But if I just pick random values of x, and I'm going to pick not super random, I'm going to pick ones that are going to be on the graph here. So if I pick initially x equals 0, well, y equals negative 2 times 0 plus 7. So that means y equals 7 when x equals 0, which means that the point 0, 7 is on the line. That is our y-intercept. If I pick some other value, I'm going to pick a positive value and I'm going to pick a negative value. So let's say I pick x equals negative 1. Then what I have is negative 2 times negative 1 plus 7. So that gives me a value of y equals 9, which means that the point negative 1, 9 is on this line. So negative 1, 9 is here. I don't actually need to be calculating individual points because I know from the equation, I knew that already that the y-intercept was going to be 7. I can see that right here in the equation. That's the y-intercept. And I know the slope, so I can actually find points just by using the slope as well. So for example, knowing that the slope is negative 2, that could be considered negative 2 over 1. So I go down 2 and over 1, down 2 over 1. There's another point. But I can also calculate the coordinates of a third point by choosing another value of x. Let's say I do x equals 3 this time around. Actually, I'm going to go 5. So negative 2 times 5 plus 7. That means y would be negative 10 plus 7, which is negative 3. So that means the point 5, negative 3 is on the line. So I've now given the coordinates of 3 points, which are on that line. So 5, negative 3 is down here. I didn't state the coordinates, but I also know that the coordinates of this point are 1, 5, which I could verify by plugging it into the equation. I don't need to do that, but sketch the line is going to be like this. So that is the line represented by that equation. In a very real sense, absolutely every point on this line is a solution to that equation. So that equation, y equals negative 2x plus 7, has infinitely many solutions because it's not a single variable. And the solutions are all going to be the coordinates of a point, a value of x and a value of y. And this line is made up of all of the solutions to that equation. So now we're ready to consider what a system of equations is. So here we have a system of simultaneous equations. The first one, y equals negative 2x plus 7, that's the equation we've been dealing with right now. So I'm actually going to transition that same line that I had drawn up here. I'm going to draw it on these other axes. So I know that the y-intercept is 7. I know that I have points here. Here the slope is negative 2, so I can actually draw in several extra points just by going down 2 and over 1 each time. And those points are some of the solutions to that first equation, which I'm going to call equation 1 very creatively. So in blue, I've drawn equation 1. The points I've labeled on here are solutions to that, but in fact, any point anywhere on this line is a solution to that equation. This second line I'm going to draw in green. I know its y-intercept is negative 1, so that's here. And it has a slope of 2/3, so that means I go up 2 and over 3. Up 2 and over 3. up 2 over 3, up 2 over 3, and so on. And I now have a series of points, all of which are solutions to that second equation, which I am going to very logically call equation 2. So all the points that I've drawn on here that I used the slope to figure out, but also points in between. All of these points on here, this line is made up of infinitely many points, and no matter how many points I can draw, it would always be possible to find another point in between them, and that is basically where this line comes from. It's made up of an infinite number of points that are all solutions to this equation. But that leads us to this idea of simultaneous. Simultaneous equations means they both have to be true at the same time. And the place where both of these equations are true is their intersection. So that intersection is the only point that is true for both of these equations. And based on this drawing, I can tell that the coordinates of that intersection are 3, 1. What that means is if I plug x equals 3 into both of these equations, so negative 2 times 3 plus 7, y then would equal 1, or 2/3 times 3, which is 2 minus 1, gives me 1. So they both give me the same value of y for the same value of x. That is therefore considered the solution to this system. 3, 1 is the only values of x and y that will work in both of these equations at the same time. So graphically, the solution is the intersection point. Algebraically, I can use the fact that I know that these two equations have to be true at the same time. So in other words, they're talking about the same value of x and the same value of y. And since I know that y equals y, it's just a reflexive property, it's sort of self-evident, I can essentially substitute in the fact that I know that y equals negative 2x plus 7, but I also know that y equals 2/3 x minus 1. Those things have to be true because it's the same value of x. So now this is an equation I can solve. I'm going to solve it by first multiplying everything by 3 so I don't have to deal with fractions. You don't have to do that. You can work with fractions if you like. But if I multiply everything by 3, I get negative 6x plus 21 equals 2x minus 3. Then combining the x's onto the right-hand side of the equation, I get adding 6x to both sides gives me 8x. And I'm going to also add 3 to both sides of the equation to get 24. This tells me that x equals 3. Not a surprise. I already knew that x was equal to 3 from the intersection point. And then I can substitute it into either one of those equations. I've already done that work up here in red to figure out that y then would have to be 1. And this means that the solution to that system is the point 3, 1. Exactly the same solution we found graphically, but now found using an algebraic technique.